Make sure I record this time. Okay, so starting chapter 9. And the big focus of chapter 9 is similar triangles. And so we're going to be doing lots of stuff with similar triangles. And, well, maybe start with, well, we'll get to a definition of what similar triangles are. I thought about giving you some intuition ahead of time, but we'll just jump right into it. So the first theorem in the book, I need a little lemma to prove. I don't know why they're automatically assuming this when they did their proof. Maybe it was a homework problem that you were supposed to do somewhere along the way. But so before I do this theorem, I need to do a quick lemma. And the lemma is that the opposite sides of a parallelogram are congruent. So in other words, if A, B, C, D is a parallelogram, meaning those two sides are parallel and those two sides are parallel, that's what I mean by those arrow tick marks. 2 tick marks is saying those two are parallel, 1 tick mark saying that those two are parallel. So if I have a parallelogram, then its opposite sides are congruent. In other words, AB is congruent to CD and AD is congruent to BC, is what I'm proving in this lemma real quick. With me? So it's a really easy proof, but just wanted to go over it because I'm going to need it over there. So first off, we have this parallelogram. First thing I do is I draw this diagonal AC. Okay? And now, this angle and this angle are opposite interior angles. The way you're used to seeing it is when I have parallel lines like this and I draw a line like that, then that and that are opposite interior angles. This time my parallel lines are kind of turned this way. But you see how it's still the same thing? That angle and this angle are opposite interior angles. And therefore they're congruent. Remember that proof from last time? Oh, you didn't even watch the lecture?
No, I didn't. Well, wow. I had time, but...
Of course you had time.
I was going to today, but today I didn't have time.
Yeah, you did. Wake up earlier. Anyways. So, those two sides are opposite interior sides, or alternate interior sides, and so they're congruent. Same thing here. These two are alternate interior sides. You have these parallel lines, and then this diagonal is a transversal going through both of them. So that angle's congruent to that angle, and for the same reason, this angle's congruent to this angle. With me? So now these two triangles that I've split this parallelogram into are congruent by angle, side, angle. They have an angle the same, they are obviously both sharing the diagonal, and then they have angles the same. So that's exactly what I'm saying over here. Angle BAC is congruent to angle DCA by opposite interior angles. Similarly, with BCA being congruent to DAC. And then finally, AC is congruent to CA. They're both the same line segment. So you get those two triangles are congruent by side, angle, side. And therefore, BC is congruent to DA, and BA is congruent to DC, which is saying that those two sides are congruent. Therefore, opposite sides of a parallelogram are congruent. Good? No questions about that? Didn't want to spend too much time on that because it's just a side note. So now we'll start this proof. I kind of cut some of the words out of the proof, out of the theorem, specifying where exactly these points go. Give me that on the picture to finish explaining. So if we have three parallel lines, L, L prime, and L double prime, so these are all parallel to each other, and M and N prime, M and N prime are two lines that cut this, or two transversals. So in other words, M and N prime are not parallel to these lines, and not necessarily parallel to each other. They could be. That doesn't change anything. And M cuts these, cuts L at A, cuts L prime at B, and cuts L double prime at C. And similarly, M prime cuts at A prime, B prime, and C prime. So when we have this picture, and if we know that AB is congruent to BC, then A prime B prime is congruent to B prime C prime. Does that make sense, what we're trying to show? We're given this, we're trying to show this.
show that A prime B prime is congruent to A B?
Oh, thank you. No. A prime B prime is congruent to B prime C prime. Did I write it wrong before? A B is congruent to B C, and we're trying to show A prime B prime is congruent to B prime C prime. Thank you. All right. Now hopefully what I said makes sense. We know that that's congruent to that. We're trying to show that that's congruent to that.
Oh, okay.
Okay?
Yeah.
That makes sense now? So erase what we don't know. This over here is what we do know. Now, what I'm going to do to prove this, find a different color, is I'm going to come, let me move A so that I don't draw through it. A is this point. I'm going to come to A, and I'm going to draw a line through A parallel to M prime. And I'm going to go to B, and I'm going to draw a line through B parallel to M prime. Now we're given by our parallel postulate that there is one and only one line through a given point parallel to a given line. Right? So I know that I can get this prime, this line, and this line. Those don't look very parallel, but they are, pictures like. And we're going to pay attention to the triangle made here and the triangle made here. Okay? So, maybe switch to blue now, red's for our parallel lines. So first off, we know that this angle is congruent to this angle because they're corresponding angles. Here's a transversal, here's two parallel lines. Those are corresponding angles, therefore they're congruent. We know that over when we're looking at this picture, we know that this angle is congruent to this angle, right? Which is going to be the same thing as this angle, which is the same thing as this angle. Good? And all for the same reason. When you look at these parallel lines, but this is a transversal, these are corresponding angles. When you look at these parallel lines, but this is a transversal, those are corresponding angles. When you look at these parallel lines, but this is a transversal, then those are corresponding angles. So we're just using the fact that corresponding angles are congruent when you have a transversal through two parallel lines. It's all we've used so far, marking all these angle congruencies. Haven't lost you yet? We're still good? All right. So now, finally, one of the theorems, I think we proved it last week, I don't remember, it might have been the week before, is that the sum of the angles in any triangle is a straight angle. In other words, the sum of the angles in this triangle and the sum of the angles in this triangle are the same thing. That's the important fact. And so we automatically know that this angle up here is congruent to this angle up here, because both triangles have to sum up to a straight angle. Good? All right. So now we've got that this triangle is congruent to this triangle by angle, side, angle. The reason we needed this angle right here was so that we could argue that these two angles were congruent. But we're not using this angle for arguing the congruency of the triangles. So by angle, side, angle, angle, side, angle, these two triangles are congruent, which gives me that this side is congruent to this side. Good? Now is where we need to use our lemma. Let me label one more point here. A, B, C, we'll call that point D. Oh, I need two more points. And point E. D and E. Now notice that, we'll look at the top one first. A, E, B prime, A prime is a parallelogram. These two sides are parallel to each other. These two sides are parallel to each other. So their opposite sides are congruent. In other words, that is congruent to that. Similarly, B, D, C prime, B prime is a parallelogram. And so its opposite sides are congruent. And we're done. Remember what we were trying to show, that this segment is congruent to this segment. You follow all that?
Yeah.
Okay, now we'll go through it again What?
I was wondering, how come you can't do lemma with a, what's the term for a rhombus? Like, how come you couldn't use two triangles for B, A prime, B prime?
B, A prime, B prime.
Put a line through it and then use those two triangles to say that AB is congruent to A prime, B prime, and then do the same thing on bottom.
Well, I don't know how you do that, because this picture right here, that shape that you just described, could look something like this. Right?
Okay.
That's a valid picture for this.
Okay. Yeah.
M and M prime could be on any angle.
I see.
They just can't be parallel to our three lines. That's our only requirement on it. And so we don't have the symmetries here that we have here. Here we have a lot of nice symmetries. Okay?
Yeah.
So let's erase the picture and write out the proof. I don't know if this proof's going to take more than this, but just in case, I'm going to give myself space over here to keep on writing. So, start out 1. Let L prime, and L double prime be parallel, and let M and M prime be their cuts such that M intersects them at A, B, and C respectively. Respectively means maintaining that order, comma, and M prime intersects them at A prime, B prime, and C prime respectively. So when I say respectively, I mean that that M intersects L at A, L prime at B, and L double prime at C, and similarly, M prime intersects L at A prime, intersects L prime at B prime, and intersects L double prime at C prime. That's what I mean by respectively. So here's our picture so far. So we've got 3 parallel lines. Namely L, L prime, and L double prime. And we have 2 cuts. At A, at B, at C for M. And then at M prime we intersect at A prime, B prime, and C prime. Okay? So now my next step was to construct 2 lines. Move A again. Maybe I'll just put A down here. I don't think I ever use that space. Our next step was to construct parallel lines to M prime through A and through B. So, shoot. Am I just going to use M double prime and M triple prime? M double prime and M triple prime. So next, 2, let M double prime be the line through A such that M double prime is parallel to M prime, comma, and let M triple prime through B such that M triple prime is parallel to M prime. With me so far? Okay. So we've got those parallel lines. Now, we need to capture this point and this point because we're going to need to talk about these two triangles. Ultimately, what I'm going to show is that these two triangles are congruent to each other. So their sides are congruent to each other. So these segments are congruent to each other. That's a big picture where I'm going with this. So let's name points real quick. We have A, B, and C. We'll call this point down here D. We'll call this point E. That's all I need. So 3, let E be the intersection, be the intersection of, let's see, that's L prime and M double prime, of L prime and M double prime, comma, and let D be the intersection of, D is the intersection of L double prime and M triple prime. L double prime and M triple prime. So now, our next step is to argue that this angle is congruent to that angle, and this angle is congruent to this angle, is congruent to this angle, is congruent to this angle. And I may kind of do that all in one go. I'm going to say that those two are congruent because they're corresponding angles. I'm going to say that's congruent to that's congruent to that's congruent to that by corresponding angles, and not bother spelling all that out because I think you know what I'm saying. 4. Then angle ABE is congruent to BCD. Oops, it's congruent to angle BCD. It's congruent to angle BCD by corresponding angles. Comma, and angle AEB,
angle A prime B prime E,
angle A prime E prime, what?
B prime E,
B prime E is congruent to,
angle B prime C prime D,
is congruent to,
angle E unmarked point D.
oh, shoot.
You just need to write that over on D. No.
Oh, yeah, wrong spot. Thank you. That's the wrong angle.
Well, it's the same angle.
No, they're congruent angles, they're not the same. Just because you're as tall as Jacob doesn't make you and Jacob the same person. Your heights are just congruent.
Okay.
Alright, so what should this last one be?
BDC.
BDC? Alright, so ultimately we should have had AEB is congruent to BDC. Perfect. So now, our next step in the argument is what?
You didn't say that.
By corresponding angles. Boom. Set.
Okay.
Alright.
Wait, C and A are 2 points, that's confusing.
Alright. So now, what's our next step? Remember, we're trying to argue that this triangle is congruent to this triangle. Oh, we know that this side's congruent to this side. Shoot.
And then,
I forgot to give that in our information. Comma, and AB congruent to BC. Oops. Right?
mm-hmm.
Okay, because we definitely need that information.
Yeah.
We need to know at least one of the sides are congruent to argue congruent triangles. So how are we going to argue that these two triangles are congruent?
You look at their sum of their angles. And some of the angles are straight angle.
We know that the sum of their angles are a straight angle. And we know that those two angles are congruent to those two angles. So the remainders have to be equal.
Yep.
Equals subtracted from equals are equal. Equals being the straight angles, subtracting those equals from it results in equals. So we know that this angle is congruent to this angle. So how should we say that? Since angle ABE is congruent to angle BCD, comma, and since angle AEB is congruent to angle BDC, and since the sum of all angles in a triangle is the same, namely a straight angle, then the remaining angles have to be the same. CBD, then angle CBD is congruent to angle BAE?
Yeah.
BA. Did I name those the same way? CBD, CBD, BA. Oh. Every time you said B, I was thinking E. I kept looking at that one. All right. So then we know that. So we know that those two angles are congruent. So then the triangles are congruent by side, angle, side. 6
Angle side angle.
by angle, side, angle, thank you. Then triangle ABE is congruent to triangle BCD by angle, side, angle. Luckily we don't have a S point, so you won't think those are points. And so what? And so this side is congruent to this side. And so AE is congruent to BD. Did I put those
Well, you want to
marks
put it
wrong?
on the triangle, yeah.
Keep doing that wrong.
You mean ES?
AE is congruent to BD. And so AE is congruent to BD. Okay, so now we've just got one more step. So then A prime B prime is congruent to AE by our lemma, which we didn't name. So I'll just say by lemma. And similarly, that's congruent to that by our lemma, right? Then AE is congruent to A prime B prime by our lemma. And BD is congruent to B prime C prime by our lemma. 8. Therefore, A prime B prime is congruent to AE is congruent to BD. That's right. BD is congruent to B prime C prime, as we were trying to show. And I'll color in the box since people are making comments about me not coloring in my boxes. All right, and we're done. That's what we were trying to show. That makes sense? Perfect. Next theorem. Let me read it and then I can think about it while I erase. Oh, I think there's two corollaries that fall from this real quick. So let's show the two corollaries before I erase this. Imagine for a second that M and M prime happen to both meet at that point, and we're tilted towards each other. Okay? So imagine our picture starting out looking like this. Let's see, and we'll call this point A, we'll call this point B, we'll call this point C. We just barely showed that if this is congruent to this, and this line is parallel to this line, then this is congruent to this. Right? So that's what the next lemma is going to tell us. It's going to tell us, like, if you have a triangle, and you know that a parallel line bisects one of the sides, split it into two equal pieces. So if you have a triangle, and you know that a parallel line bisects one of the sides, it also bisects the other side. You see how that comes for free from this? It's what we typically mean by corollary. We mean there's little to no work required to get the proof of this from what you just did. So this is one corollary from this. And then the other corollary, maybe I said that wrong. Maybe I just barely told you the second one. If a line bisects two sides of the triangle and is parallel to the, okay, here's what the last corollary says. The last corollary says, if I know that a line, so now forget that that's parallel. Let's say I know that this line bisects both sides of the triangle, then they say the resulting thing that you can conclude is that it's parallel to this one.
And another part. The middle line is half the side.
Yeah, we'll get to that, but let's wrap our head around this. So how can we get that right out the door? Maybe this one's going to take a little bit proving. Here's how you do it. I say draw a line through this point. Draw a line through this point parallel to this line. Shoot. Kind of don't want to erase that while doing this. Let me just draw a picture and talk through the proof as I go. So they say, if you have a triangle, I'll put A up here, I guess. B, C. And if you know that D right here is a midpoint, so that's segment, and E right here is a midpoint, so those two are congruent, then prove that this line is parallel to this line. Okay, that's what we're trying to do. So the first step is to just pick a line that goes through D parallel to this line. Some random line. There it is. And it intersects here at F.
Okay.
And we're showing that DF is really DE. Is that how they do that? This feels like I'm doing another proof. That looks familiar, but we'll stick with this for a second. So we know that this line is parallel to this line by construction. We picked the one line that goes through this point D parallel to this. We don't need F over here. That's fine, so just have a line to it. So there's the line that goes through D parallel to this, right? Now we know that the line that goes through D parallel to this line also bisects this side. That was our previous corollary, right? Imagine we put this line right here. If a parallel line goes through this point and bisects this side, it also bisects this side. If a parallel line goes through this point and bisects this side, it has to also bisect this side. So it does also go through E. And so that line that we drew is parallel to this line. They're both the same line. Does that make sense?
Okay, yeah.
So that's the second corollary that you get for free. And it has a second part, because now you can think about this is the base of the triangle. Or, sorry, think about this as the base of the triangle, right? And now this is bisecting this side. So, if we drew a parallel line through here, so that this is parallel to this, since it bisects this side, it also bisects this side.
Okay.
Right?
Uh-huh.
And then finally,
Parallelogram.
imagine that we had another parallel line right here, right? And so this comes through.
Okay.
This is also bisected.
Yeah.
Let's say what Mark said, that's better. So rather than that, so this is bisected, right?
Uh-huh.
And then here's a parallelogram. So that is as big as half of that. That segment is as big as that segment, which is half of this.
Oh.
So let's go through that one more time. Restart. We have a triangle. A, B, C. We have a point here which is midpoint and a point here which is a midpoint. So we know that's congruent to that. We know that's congruent to that. We choose a line that goes through this point parallel to this. So we choose a line that goes through this point parallel to this. Well, it has to bisect this side. Therefore, it goes through that point as well. Right? Now, do the same thing. Draw a parallel line to this line through this point. So that this line is parallel to this line. Same thing. Since it goes through a bisector here, it has to also bisect down here. So this, my picture's lying a lot, but that's the same size as that.
That's the part. How do you know that?
It's the exact same thinking. I drew a line through here, parallel to this bottom line. Since it went through a point that bisected this side, it has to bisect this side. Same thing. Draw a line through here, parallel to this line. Since it bisects this side, it has to bisect this side.
Okay.
We did the exact same thing. We just turned and made that the base and redid the exact same thing again.
Yes, but you had given on AC that those two lines were going to be congruent. You don't have that given on BC.
Okay, so let's ignore the first part of the proof then and do this again. Probably should have just erased this and drew it all out. Alright. A, B, C. Let's just say that we start with the point here. That is the midpoint of this. That's all we got. Then I draw the line through here, parallel to this. So that this is parallel to this. Using this theorem up here, I know that wherever point this hits, bisects over here.
Okay.
Repeat. I know that this is the midpoint of this segment. Draw a parallel line through it, so that this line is parallel to this line. Since it bisects this segment, by this same theorem, it has to bisect this segment.
Okay. So it's the exact same thing.
It's the exact same thing. You just tip the picture and do it again.
Okay.
And so this is a parallelogram, and opposite sides of a parallelogram are congruent. So that segment is congruent to that segment, which is half of this segment. So in short, if I gave you some picture of a triangle real quick, and I told you that this distance here was 1, this distance here was 1, and this distance here was 2, you instantly know that the base of this thing is 4. Oh, and if I also told you that this is 3/2, and this is 3/2, I guess. This distance is double that distance. And we could have done the same thing. We could have drawn this line, and we know that this distance is half that distance, and we could have drawn this line, and we know that this distance is half that distance. Does that make sense? It is cool. It's a lot of information you can instantly start taking out of these triangles. Right? Don't you wish we would have done cool stuff like this in trig? Right.
James wishes he had it for 5th grade math.
Yeah, there's no reason that this kind of stuff can't be taught to a 5th grader. Just work their foundations up. One of my teachers, he experimented with that, and he went and he took a 6th grade class, and I think it was over the summer or something, and he taught them, they show up for a couple weeks, Tom graph theory, just to prove it could be done. The person responsible for the students asked him where he got all this material. He says, that's what I'm teaching my college students. She's like, are you crazy? You're just teaching a 6th grader college math? There's no reason you can't. Math just builds on itself. If you understand what you start with, you can understand where it goes. You just need to have the logic and reason. It's the beauty of it. All right. So that is that theorem and those two lemmas. Very useful. Tons of information that we can start to get out of those. Similar triangles is typically when people start getting lost in how to do proofs in this class, in geometry. Everything kind of feels like it's a little bit straightforward. There's only a couple ways to do it. Like a lot of your proofs could only be done with like side angle side or side side side, and you're looking for really basic things, we're going to get to the point with similar triangles where there's just so much information that you can extract out of that thing, it's hard to know for sure how to begin doing that. There's only one way to get good at it, that's to do it. There's no tricks, nothing you can memorize, you just got to start doing it. Which means in short, do I need to yell it? Okay, you get it? Okay. Alright. It is warm in here. Did the AC stop working? You want to go see if that's just like turned off or something? Is it warm to you guys? Or is I'm just dying because I'm yelling?
Does yelling make you hot?
Yeah!
Oh, better stop.
Maybe I like being a little warm. Or maybe I'm willing to suffer for the sake of your education.
I'm not.
You're not? Yeah, I gotta fix that. Okay. Oh, construction 9.1. It's not a theorem, but it's construction. So you might recall going way back to when we first introduced the Archimedes Principle. You remember the Archimedes Principle or the Archimedes Postulate at all?
No. Well, I'll probably
Is that the
remember
one that
when
the
you
lines
explain
build
it.
on each other?
It's the one that made so that we can go as far in a particular distance as we wanted, but it gave us more than that. It basically said, for any segment you pick, we can find a number that gives you the length of that segment. So the Archimedes postulate basically told us how to go from a segment to a number that represents the length of the segment. And then the completeness axiom said that for any length you have, you can create a segment that long. Those were what those two things were. Anyways, in going from a segment to the length of the segment, one of the things we did is we said, okay, so let's pretend that here's the segment that we want to measure. How do we do that? We pick whatever we want our units to be. We start counting off whatever those units are. So here's one of those units. We do another one of those units. So maybe I won't put a tick mark there to show it's congruent, but we do another one of those units. 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 Oh, we got past it. So now it's like we zoom in on this thing, and we break that thing up into tenths. And so we break that thing up into tenths, however many we get, and oh, it went 3 and then some. So far our number that we're making is 1, 2, 3, 4, 5. 5 point, and then it was 3, zoom in, split into tenths, do it again, and you get 2, zoom in, split into tenths, do it again, 5, etc. And you get this decimal number representing the length of this segment, right? Do you remember that?
No, I don't.
Well, we did that. But one of the problems we had at the time is we didn't know how to divide up a line segment into 10 pieces. If I said, here's a line segment, AB, divide that up into 10 pieces, or into 5 pieces, or into 3 pieces, might be hard for you to do. You could probably figure out how to divide it up into 2 pieces. That's not so hard. You know, you take your compass over here, you construct this circle. You take your compass over here, you construct this circle. Wherever those 2 circle points intersect, draw that down, it bisects the line. But what if I want you to split into n equal pieces? How do we do that? That's what our next little thing's going to be. And it's a construction, not so much a theorem. But we'll go over how to do that. And we already talked a bit last time about how constructions are using our theorems, right?
I don't remember that.
Not last time, but the time before. Sorry. 2 times ago, if you were there. It was the lecture that I thought got erased, but didn't actually get erased. But the end of it got randomly cut off. And we talked about Euclid's theorems? Yeah. Anyways, so let's go over how we do this. So let's say that I have some segment, AB, and I want to divide it into how many equal pieces?
7.
7. So what I heard was 5. So we draw some really long line, make sure it's long enough for whatever you need. We set our compass to any length we want, and we start marking off equal distances of that length, right? So I go and I mark off 1 of those lengths, 2 of those lengths, 3 of those lengths, 4 of those lengths, 5 of those lines. Okay? And then, mark that point, I create this triangle, like that. And then, through each of these points, I create a line parallel to this line. Now, we're in a lot of trouble because I can't draw worth anything. And so I don't know if this is going to look good when we're done, but I'll try to make it look somewhat decent. Oh wow, that has a notch. You can see I'm not doing too good of a job even with a ruler. Oh well. But you get the idea.
It's because your distances weren't the same.
Oh yeah. Yeah, probably should have marked those out good if I was going to do these good. Anyways, the point is all these lines are parallel now, right? And I also know that all these segments are congruent to each other by construction, right?
Yeah.
Now, you can think about looking at just these two pieces. I have a parallel line that bisects this line segment, and it's parallel to these lines, so it has to bisect this line segment. So now this piece is congruent to this piece.
Okay.
Look at these two, same argument, that's congruent to that. Look at these two, that's congruent to that. Look at these two, that's congruent to that. So now I just divided AB up into 5 congruent pieces. You see that?
Uh-huh.
You feel like you could do that with a straight edge and a compass now?
I don't believe it. For some reason, it's thrown me off.
You don't believe it's true?
Yeah, I don't believe it's
Last
true.
triangle.
It's kind of thrown me off.
Well,
maybe it's just
I
kind
drew it
of
real
things-
bad. You could look in your book on page 157 and they have a better picture of it.
Yeah, I look at it and I still don't believe it's true.
You still don't? Alright.
I'll go home and do it by myself.
Yeah, go home and try it. Because it's just going to require me to draw a more perfect drawing.
Yeah.
But if I were you, I would make these very extreme, and then these ones not so extreme. And then measure it. And I would only do like 3 pieces, because if you see it for 3, you're going to see it for all.
I'll do 7.
Well, if you want to do that much work, okay. But it has to be true, because our theorem was true. Did you have a problem with the theorem? Then how do you have a problem with the construction? All I did was use the theorem.
Picture. It's lying to me.
Don't trust the picture! Pictures lie. We know that.
Yeah, I can feel it.
You can
We
feel
don't
it?
know
You feel it in your left bone? I know it. I don't know if you know it.
that. I haven't proved it.
We haven't proved that pictures lie.
What if they tell the truth?
What if they tell the truth?
Okay, now exchange that number for 92 point.
It's not hard to make a picture lie.
Yeah, the same picture is slide. Why is all the pictures up? Nothing.
Well, it depends on how you want to interpret that. You're talking about how you use the English language. And we don't care about English in this class,
Pictures can lie.
except for to the extent that we need it. Then we come up with precise definitions.
Well, when they did geometry with just pictures before.
Well, they were very precise about how they drew things. And yes, there is criticism about how Euclid did geometry. That's why Hilbert created these axioms and these postulates.
But
He says we need to get real precise about what exactly you're talking about. Because sometimes things that appear obvious to you aren't obvious when you take your time to do the math. One quick example from calculus, you know the product rule. And Leibniz, when he was developing calculus for 10 days, he had a note in there that he says, and obviously the derivative of the product is a product of the derivatives, which is not the case. Now, he had that in there for 10 days, realized his mistake, but it's now recorded in his notes that at one point there was a 10-day period where he said, obviously, the derivative of the product is a product of the derivatives. And so it's real easy to make a mistake when you don't force yourself to be all the way precise. And it's also limiting in a way. You can't figure out what else you can do when you haven't been precise enough. All right. Moving on. So that was construction 9.1. All right, definition 9.1. A ratio. We've already talked about ratios in the algebra reviews, but what's a ratio?
Mark, that's you.
In short, it's a rational number. That's what a ratio is, a rational number. So x over y, we say, is a ratio. Sometimes you say x divided by y. Okay? When we say that two ratios are proportional, maybe give you an example real quick. 1/2 and 2/4 are proportional ratios. So when we say two ratios are proportional, here's how we might say this. We might say xy is proportional to x prime y prime. What does that mean? That means x over x prime is equal to y over y prime. Or we could have said x prime over x is equal to y prime over y. Both those are saying the exact same thing. If 1/2 equals 2/4, that's logically equivalent to 2 equals 4/2. Flipping the reciprocal doesn't change the fact that the proportion is still true. Do you see that? And so if I would have written this out in some big thing, if I would have said x, y, z, a, b is proportional to x prime, y prime, z prime, a prime, b prime, then that's just telling you x over x prime is equal to y over y prime is equal to z over z prime, etc. That's what it means to be proportional. It means their ratios are equal. If you take that over that, it's equal to that over that, it's equal to that over that, it's equal to that over that, etc. Feel like you understand ratio and proportional? Okay. So, theorem. And some of these theorems we already did in the algebra review, but no harm in doing them again. Oh, we need another definition. If b is not equal to 0, then a over b is the number q. All right.
Hey, I know this.
Yeah, we did this in the algebra review. Now he's formally using it, so good thing we did the algebra
No,
review.
discrete mathematics.
Oh, yeah, but there was a remainder in that. So if b is not equal to 0, then we say a over b. What's the definition of that? That is the number q such that QB is equal to A. Did I draw my fraction different than they do? Oh, they just say A is equal to QB. So saying A divided by B is, if A divided by B equals Q, if Q is that number, A divided by B, that's logically equivalent to saying that A is equal to QB, or BQ. Right? We defined our division in terms of multiplication when we were doing our algebra review. So that's nothing new. We've already seen that. And we've got some theorems that we already did in our algebra review. They say, I'm not going to write this out, I'll just show the math. So we're going to prove that A over B is equal to AC over BC, right? So A over B, that's a number Q, right? So then, so this gives us A is equal to BQ, right? So AC is equal to BQC, or BCQ. So Q is equal to AC over BC. We're kind of chugging along that. This is the definition of whatever that symbol is. That is the number Q such that B times Q equals A. Then we know we can multiply both sides by the same thing. That was one of our axioms. And then this is using the definition once again. If that thing times that is equal to that thing, then we can rewrite it like that. We can go from this to this, however we want. And we can go from this to this whenever we want. So, Q is equal to AC over BC, and Q is equal to AB. We didn't really specify that. Probably should have said let Q equal A over B, well then A equals B times Q, AC, etc. Good? Going a little bit faster because we already did this. Right? If neither B nor D is equal to 0, A over B equals C over D if and only if. Alright, let's just write it. Prove A over B equals C over D if and only if AD is equal to BC. Okay? So I need to show this implies this, and then this implies this. Well, let's start with this. So if I have A over B equals C over D, multiply both sides by BD, and that gives me ABD over B is equal to CBD over D, which gives me AD is equal to BC. Now if I have AD is equal to BC, what can I do? I can multiply both sides by one, right?
I'm not getting it.
Just reverse the steps. What I do to go from here to here, I canceled out the B's with the B. I canceled out D and D and B and B. So now to go from here to here, multiply this by 1, namely D over D, and multiply this by 1, namely B over B, and you have this. Right? Now divide both sides by DB, and you have this. So nice thing about what you did in algebra, every time you do something algebraic, you're doing an if and only if proof. Because they can go forward and backwards, unless you start introducing inequalities. But when you're always using equal signs, you can just go back and forth like that. So it's real easy to do if and only if proofs. So every time you had, for example, 2x equals 4, then you said x equals 2, that's an if and only if proof. You showed that if this is true, then this is true, and if this is true, then this is true. Because you can just reverse the steps. That's all we did. Here we did one set of steps, here we reversed them. Just simple algebra, right? And then finally, there's one more. We can rewrite let me just show the final thing. So AB is equal to CD is logically equivalent to AD is equal to BC is logically equivalent to AC is equal to BD. Okay, that's the last thing I'm going to show. Now if we have A over B is equal to C over D, multiply both sides by BD. Multiplying both sides by BD, what do we get? We get AD is equal to BC, same thing we did up here. Oh, I just canceled out one step. Are you okay with me canceling out one step? And now, what do? We divide both sides by CD. Divide this by CD, that leaves me A over C. Divide this by CD, that leaves me B over D. And obviously we could reverse our steps. And so we can interchange between thinking about these ratios in any of these ways, and it's perfectly valid. If you know A over B equals C over D, you know that AD equals BC, and you know A over C equals B over D. Let's do this with some numbers real quick. So if I know that 2/7 equals 4/14, I know that 2 times 14 is equal to 4 times 7, and I know that 2 over 4 is equal to 7 over 14. You see all that? So there's a lot of different ways that we can use these ratios, however the math comes out best for us, however it's most intuitive for us to think about it. But those are all the same. Good? Yeah? All right. Oh, I guess I combined theorem 9.3 and theorem 9.4 right here. But, so they're both done. All right. Ratios and proportions in geometry. So this was all side notes for talking about algebra. Now let's bring this back to geometry, talking about lengths. If you think it's going to be a big castle, you don't have to worry about it. We can just open windows.
No, something's up with it.
You think it just blew that same capacitor again?
I have no idea what's going on.
Well, maybe we should open some windows, because it's boring. Just lift the doorknob up on the belt rack on the back. That's too bad. Had AC for like a year. Pop-ups. All right. So now, talking about ratios or proportions in geometry with side lengths. So let's go over definition 9.3. So it says, if AB and CD are side lengths, the ratio AB to CD, the ratio AB to CD is the number AB over CD, right? AB over CD. Now remember when we put that line segment above, we're talking about the number that represents this thing's length in terms of some sort of units. Okay? So if AB and CD are segments, the ratio AB to CD is the number AB over CD. The statement that the segment AB and CD are proportional to segments A prime, B prime, and C prime, D prime means, all right, so let's write this out. To say AB and CD are proportional to A prime, B prime, and C prime, D prime means that, I think they do AB in the numerator, try to copy what they do. Yeah. Means AB, its length, over A prime, B prime, is equal to CD's length over C prime, D prime's length. That all make good sense? Same thing we were saying with numbers? Now, of course, based off of our properties, we know there's a couple different ways that we could write this. I could swap those two number places, or I could say that times that is proportional to that times that. Right? You already lost that? You got that? That makes sense? Okay. And then we can say that, when we say that a triangle, if I say that triangle ABC is proportional to triangle A prime, B prime, C prime, what am I saying? I'm saying AB over A prime B prime is equal to AC over A prime C prime is equal to BC over B prime C prime. Saying all its sides are proportional to all its sides, respectively. Does that make sense? So note once again, saying triangle ABC is proportional to this is not the same thing as saying it's proportional to triangle C prime, B prime, A prime. Order matters. Does that make sense? And this is going to be one of the things that we used to talk about, similar triangles. In fact, I think we're ready now to talk about similar triangles. Alright, they take a while to talk about similar triangles. I want to talk about similar triangles to motivate why we're doing all this real quick. So, you have intuition for what similar triangles are. What's your intuition?
Their sides are this or are proportionate.
Let's just start with two pictures. You would say that this is probably similar to, or you would say that this probably isn't similar to this. Let me give that more of a slant in case you think I was trying to draw it. You would say this isn't similar to this, but this might be similar to this, right?
Mm-hmm.
And so what we mean when we say that this is somehow similar to this, we're saying this is like a scaled down version of this. Or that this is a scaled up version of this. That's kind of the way that we think about that, right?
Mm-hmm.
And so if this has lengths 3, 4, and 5, and I tell you that this one has length 1, then you expect this side to be 4/3, perfect. And you expect this side to be
1.6.
5/3. Yeah. So we took this thing and we scaled it down by a factor of 3, right? We made that 1/3 its size, that 1/3 its size, that 1/3 its size. And in the process, we kept all the angles congruent, right? So that angle is still the same as that angle. That angle is still the same as that angle. And let's pretend that this was a right angle. So we kept the angles aside the same, but we scaled it down or we scaled it up. And notice that these things' sides are proportional. So in other words, 4 is proportional to 4/3. Let me do this is proportional to this, so that our fractions are in the numerator. You okay with that? So this side is proportional to this side. We're saying 4/3 over 4 should be equal to this side proportional to this side. 1/3 should be equal to this side proportional to this side. Right? And if I take 4/3 and I divide it by 4, that's the same thing as 4/3 times 1/4. And 4/3 times 1/4, 4's go out, that leaves us 1/3. Which is 1/3, same thing here. 5/3 divided by 5 is the same thing as 5/3 times 1/5. 5 and 1/5 go out, we're left with 1/3. Do you see how all those are equal?
Mm-hmm.
So we're going to say two triangles are similar if all their angles are congruent and all their sides are congruent respectively. In fact, this isn't how we're going to say triangles are congruent. This is how we're going to say convex polygons are congruent. Or sorry, similar. We're talking about similarity. So this triangle is similar to this triangle. That's what we mean. And in a similar way, we can talk about a square being similar to a square, or a rectangle being similar to a rectangle, or a pentagon being similar to a pentagon. Do you see how we would generalize this? This is why we care so much about proportionality. Now we're going to find out later that for two triangles to be similar, you just have to require that their angles are congruent. And then the sides are automatically proportional. That's not the case in general. So that's why our definition of similarity with triangles is including both these things that we don't necessarily need for triangles, but we need them for other polygons. So we're just using the same definition for all polygons that we're going to be talking about. Does that make sense? No? We'll get to it again. We'll take this again as we come up. But that's the reason that we're spending so much time talking about proportionality. It's going to help us with talking about how things are similar to each other. So, there was our definition. say that the ratio of AB to CD, that ratio is represented this way. To say AB and CD are proportional to A prime, B prime, and C prime, D prime means to say that those are equal. And then similarly with triangles, to list out their three sides equal. Right? So that's definition 9.3. So moving on to theorem 9.5. I'm not going to prove this one. Just show you, because the author's proof of it isn't all that rigorous anyways. He's saying it doesn't matter what units you have for proportionality, it's always the same number. So for example, if I have 13 feet over 2 feet, that is equal to 13 halves, which is also equal to 13 inches over 2 inches, which is also equal to 13 miles over 2 miles. In other words, the units don't matter, our ratio is always the same. Because whatever the units are for the top is what the units are for the bottom. And in short, the generalization of this is 13x over 2x is equal to 13 over 2. Doesn't matter what those units of x are, as long as they're not 0, right? And we don't have a concept of a zero length segment. There's no such thing as a zero length segment. Segment is two distinct points and all the points between them. So it doesn't matter how long our segment is that we're calling our unit, whatever our unit is. If it's a foot long, if it's an inch long, if it's a mile long, the ratio of those two things is always the same. That's what that's saying. So that's theorem 9.5. And then he makes a mess of terminology for one proof that I don't like how he does it, but we'll follow it. And if there's time at the end, I'll do the proof the way I want to do it. All right, definition 9.4. One segment is said to be commensurable with another if the ratio of the first to the second is a rational number. So what does that mean? That means if this is 3, this is 5, and this is 4, then the measure inches, we'll give them some unit, then the ratio of this side to this side is just 3/5, right? And so if it can be represented as an integer over an integer, it's called a rational number. And remember how we proved how any infinitely repeating decimal can be represented as a rational? So if it can be represented as a decimal number, it doesn't matter, as long as it has repeating decimal somewhere, it doesn't matter if it's 6.000 repeating, or if it's 6.111 repeating, or if it's 6.123 and that repeats over and over again, 1 2 3 1 2 3 1 2 3, then we can always represent it as a rational number. We can represent it as a fraction of two integers. So if the ratio of this side to this side can be represented as a rational number, if that ratio can be represented as a rational number, then we say that they are commensurate. What's an example of one that can't be? You might be wondering right off the top of your head. Let's think about a square for a second, with side lengths 1 inch, I guess. And then this side, with that nice curve in it, has a length of?
A little more than the square root of 2.
My picture's lying. That's a perfect line from that point to that point. It has a length of the square root of 2 inches, right?
Mm-hmm.
And so this side and this side are not commensurate. You cannot represent the ratio, square root of 2 over 1, as a rational number. You'll never find two integers that work to represent that ratio. And you should know, we proved that the square root of 2 is irrational. Right? You remember doing that? Discrete math?
Yeah, I remember doing it.
All right. So, that's what he's defining as commensurate. So let me read the definition one more time. One segment is said to be commensurable with another if the ratio of the first to the second is a rational number. They are said to be incommensurable if the ratio is an irrational number. Here's one that works. Here's one that doesn't work. Good? Okay. Now, a theorem. Two segments, AB and CD, are commensurable with each other if and only if there is a segment EF which, if used as a unit of measure, makes the measure of AB and the measure of CD whole numbers, or integers. So let's do that proof. So let's write down what he's saying. Two segments, A, B, and CD, are commensurable with each other. What does that mean?
The
Their
ratios.
ratios are rational.
Right.
numbers.
So write up what theorem this is real quick. Theorem 9.6. Theorem 9.6. So we're saying that AB over CD, that distance, now I'm going to use some notation, I don't know if I've used it in this class or not, is rational. How do we say that's rational? We say that's in the set of all rationals. This little symbol, this backwards E looking symbol, means it's in the set, and that is shorthand for the set of all rationals. Let me give you an example of using this notation. 2 is in the set 1, 2, 3. That is an element in there. 2 is not an element of the set 1, 3. There's examples of using it. This set has an infinite number of things in it, so we have a nice shorthand for representing all possible fractions right there. A Q with an extra line on the right hand side. Okay? So this ratio is in Q is the same thing as saying that these two are commensurable, right? So now let's read what the theorem is saying again. Two segments, A, B, and CD, are commensurable with each other if and only if, so that ratio is in Q, if and only if if and only if there exists a segment, backwards E, there exists a segment,
Forwards E.
EF, give it lots of space so we don't get confused. If and only if there exists a segment EF which, if used as a unit of measure, makes AB and CD whole numbers, makes the measure of those whole numbers. So if there exists a segment EF such that AB is equal to M and CD, the measure of AB is equal to M and CD is equal to N, where M and N are integers. So once again, we're saying those things are in the set of all integers. This is a set of all integers. This is a set of all rationals. Let's read that one more time to make sure we make sense of it. The ratio of the length AB to CD is a rational number if and only if there exists some unit of measurement such that the measure of AB is an integer and the measure of CD is an integer.
I'm confused with some unit of measurement.
Okay, so I say this is 0.5 feet, and I say that this is 0.5 feet.
Then what's EF? Like,
F is 1 feet.
EF is 1 foot. Okay? 0.5, is that a whole number? 0.5, is that a whole number? No, so pick a different EF. This EF doesn't work. Well, what if we make EF instead of 1 foot, 1 inch? Well, what does that make this and this? 6 inches. And 6 inches. So these sides are commensurable. Because there was some unit that I could find that made this an integer and this an integer.
We aren't going to worry about that, right?
We're going to show that if this over this is a rational number, which it was before, it was 0.5 over 0.5. What's 0.5 divided by 0.5? 1. Is 1 a rational number?
Yes.
Yes. You can represent it as 1 over 1. Rational number. So that was a rational number. So that meant that there should be some EF, namely 1 inch, such that we can make that and that integer lengths. So that's thinking about that way. And then if we can find integer lengths, obviously an integer over an integer is just irrational. So going from this to this is trivial. Going from this to this is the only one where we have to think. So maybe we'll prove this way first. 1, that's an arrow pointing this way. In case that looks all funky. I don't know. Alright, so pointing this way first. So let EF exist such that the measure of AB is equal to M and the measure of CD is equal to N, where M and N are integers. Good? 2. Then AB over CD is equal to M over N is irrational. We're done. We showed that if this is true, then this is true. Now we need to go the other direction. With me? Okay. Now proving this way. So 1, let AB and CD be segments such that AB over CD, that length, is a rational number. Mark the pen down on me. Try blue. With me so far? So we're picking out two lengths such that the ratio of those lengths is a rational number. How can we know that the ratio of those lengths is a rational number if we don't know our unit yet? We just barely showed units don't matter in the previous theorem for showing that the ratio is the same, right? We just showed that if the ratio is 7/2, it doesn't matter what the units are. That can be 7 inches to 2 inches, that can be 7 miles to 2 miles, that can be 7 whatever to 2 whatever. So it doesn't matter what your unit is when you're talking about the ratio. If I draw a line and I draw a line and that's 7 times as long as that, it doesn't matter what our units are. So we have two segments, whatever they are, such that the ratio of their lengths is some rational number. Now, what does it mean for it to be a rational number?
The numerator and denominator are integers.
They can be represented as integers. That means that we can represent this as two things are integers. Now, keep it, you had the right idea, but I want to show the technicality. This could have been 2/3 over 5/3, for example. That's not an integer, that's not an integer. But this is still a rational number. Why? Because it's the same thing as 2/5. So it's not saying that this is a whole number, and it's not saying that this is a whole number. It's saying that there is two whole numbers that we can put one over the other and say this thing's equal to it. That's what it means to be rational. Does that make sense? Another example that just to help stress this could have been 2 square roots of 2 over 3 square roots of 2. So it didn't even have to be irrational over irrational. It's just that the quotient has to be irrational. Because this just comes out to 2/3, right? Which is, once again, rational. You see the technicality I'm trying to capture? But I think you have the right thought. So 2. Then there exists 2 integers. We don't know what they are. 2 integers. What should we call them?
M and N.
Oh, that's a good choice. M and N. So there exist 2 integers. Then there exist M and N in Z, or there exist 2 integers M and N, such that this ratio AB over CD is equal to M over N. Right? Three. Now we need to show that if this is true, then we can find an EF that makes this and this true. So we need to come up with EF. That's what we're trying to find. Am I losing you? Trying to think of another example off the top of my head. So if this were, for example, 2 square roots of 2 over 3 square roots of 2, then maybe inches, then maybe the EF that we want is square root of 2 inches. See, if EF is square root of 2 inches, then this is now 2 EFs, and this is now 3 EFs. Right? So we're saying, look, this thing right here can be represented as a rational, right? Namely 2 over 3. So now we need to figure out the EF that makes so our units are 2 over 3. So what's the EF that we want in our case?
Some random length.
Well, what is this compared to this?
2 times.
Yeah, this is 1/2 of that. And this is 1/3 of that. So we need 1/n of this, or 1/n of this. And then MEFs get you M of them. Right? If we make EF 1/n of this thing, then MEFs gives you back this thing. If we make EF 1/n of this thing, then NEFs get you back this thing. So if we make EF 1/n or 1/n of that, then this is now MEFs and this is now NEFs. And we know how to do that. So we need to take AB and divide it up into M pieces and pick one of those segments and make that EF. Or we need to take CD, divide it up into N pieces, pick one of those segments and make that EF. Do you see how to do that? Do you see what I'm saying there? This is a lot of work that he's doing to set up one proof that I really don't like that he goes through all this. But it's good thinking and good for you to think about rational numbers, especially for those of you going on to algebra. Or retaking discrete math because you failed.
We're retaking algebra.
All right. So, next, let EF be 1/n. You good with that? I've never written that before. 1/n of AB. Good? So in other words, here's AB, divide it up into n pieces, and let EF be one of those pieces. Doesn't matter if it's this one, doesn't matter if it's this one, just let it be one of them. Let EF be 1/n of AB. 4. Then, AB's length now in terms of EF is M, and CD's length now in terms of EF is N. And we're done,
Wait.
which are integers.
CD's length in terms of EF. EF is 1/n. So I'm confused because you wouldn't EF for CD be 1/n?
Look, back to here. When I took this segment and it came out to 2/3, I knew that I need to make this either 1/2 of this or 1/3 of this. Doesn't matter.
Okay, I see.
I needed to make EF either 1/n of this or 1/n of this. Those two things are the same size because this ratio has to be maintained.
Yeah, okay.
1/n of this has to be 1/n of this. Otherwise, this isn't true. Does that make sense?
Yeah.
In other words, 1/2 of this has to be 1/3 of this. Otherwise, this thing isn't, the ratio of this to this isn't 2/3. Or in other words, 3 of these has to equal 2 of these. Cross multiplication, maybe that's the way to see it. Cross multiply, NABs has to equal MCDs. Is that helping? I don't know. But that's the proof. Do you see where we're done? We showed that that is an integer now, and that is an integer now. Good? If there's any questions, I mean, it's not like we're in a hurry.
I just can't think of any.
You can't think of any questions? Well, if you go home and watch the lecture and you can think up questions, feel free to bring them next time as well.
Or comment on the YouTube channel.
Or comment on the YouTube channel, and I'll get back to you.
Don't say that.
Smash that like button,
So that was Theorem 9.6. And then definition 9.5, we went over what it means for two things to be similar. Let's read that definition one more time. So, definition 9.5. So two triangles are said to be similar to each other if corresponding angles and corresponding sides, if corresponding angles are congruent and corresponding sides are proportional. So definition. Triangle ABC is similar, that's our symbol for similar, it's congruent without the equals, to triangle A prime, B prime, C prime. That means that if and only if, it's a definition, angle A is congruent to angle A prime, angle B is congruent to angle B prime, angle C is congruent to angle C prime, AB over A prime B prime is equal to AC over A prime C prime is equal to BC over B prime C prime. These 6 things have to be true to say that that is similar to that. And then for any convex polygon, we just expand the angles that we say are congruent and we expand the sides that we say are proportional. Does that make sense? So if we were talking about a 4-sided figure, I'd say angle D is also congruent to angle D, and I'd say, depending on where I stuck the D, this is also equal to AD over A prime D prime. Does that make sense? Good with that? Okay, so that's our definition of similar. Now the big theorem. Theorem 9.7, the reason that we went through all this commensurable nonsense. Theorem 9.7. Alright. if the angles of one triangle are congruent respectively to the angles of another triangle, then the triangles are similar. So in short, what we're trying to show, let me draw two pictures. Maybe give myself a little bit more space there. We'll make this a big one. A, B, C, and then some other triangle. A prime, B prime, C prime. So what we're saying is that if the angles, we'll use 3 there, 2 there, 1 there. If the angles are congruent, then these triangles are similar. So what do we need to show? We need to show that A prime B prime over AB is equal to B prime C prime over BC is equal to A prime C prime over AC. That's what we need to show. We've already got that the angles are congruent. For similarity, you need the angles are congruent and the sides are proportional. Now, showing that one side is proportional to another side is identical for showing that one side is proportional to another side. So we're only going to bother showing this side is proportional to this side. Meaning that over that is equal to that over that. That's all we're going to show, but showing that that over that is equal to that over that is identical. Okay? And the author says, I want to use his exact verbiage. In forming the proof, we will suppose that the segments AB and A prime B prime are commensurable. In other words, they can be represented as a ratio, a rational number. In other words, he says the exact same thing as me. In other words, AB over A prime B prime is a rational number. The proof for the incommensurable case is difficult since it involves knowing about limits. Now that's just not true. There's another proof for this that requires you to know about areas that you don't need to know about limits for. Maybe he just didn't know about it and that's why he went through all this nonsense of we're only going to prove one case. But so we're only going to prove the case where they are commensurable. And then if we have time at the end of class, I will prove it using area. The reason I'm not going to prove it using area right out the door is because we haven't talked about area yet. And I'd have to jump through a lot of stuff to get to the point where I could just prove this. But so I don't know why he does it that way. You absolutely do not need limits to prove this theorem is true. You just need area. And maybe he didn't want to go from similar triangles to area, and without area, you have to use limits. I don't know.
The next chapter is area.
The next chapter is area. Maybe he'll come back to this theorem and prove it with area. But, so we'll continue. So now we'll do it the way that he says to do it. We're going to assume, all right, let's say, given that angle A is congruent to angle A prime, angle B is congruent to angle B prime, angle C is congruent to angle C prime, and this are commensurable, and A prime B prime over AB is a rational number. So given that, prove, I'm not really writing this as a theorem. If, what am I doing? If that is true, then triangle ABC is similar to triangle A prime, B prime, C prime. Good? Okay, big picture, how are we going to do this? Switch to color to draw our picture. Let me think. So, first thing I'm going to want to do is construct a point over here so that it's congruent to this segment. So pick D over here so that this is congruent to this. Okay? And then, let's see what I may want to do. I may want to construct a line through that point so that this line is parallel to this line. And I know I can do that with the parallel postulate. Then, this and this are corresponding angles. So I know that this angle is congruent to this angle. Now I have this triangle is congruent to this triangle. Right? And so now all I need to show is that this triangle is congruent to the big, or this triangle is congruent to.
It's similar.
Thank you. This triangle is similar to this triangle because this is congruent to this, and so this is already similar to this. So if this is similar to this, then we're done. Okay? So that's a little bit of work to do that. Now, because this is in Q, then I know that there exists some EF. Maybe I'll kind of outline the proof here. I don't want to take all the time writing it precisely. So 1, let D on AB such that AD is congruent to A prime B prime. Maybe I should stop for a second and clarify a few cases that we don't need to worry about. I just barely made this triangle bigger than this triangle, arbitrarily. Right? So first off, if these two triangles were the exact same size, in other words, all I really assumed is AB is bigger than A prime B prime. So first off, if A prime B prime were exactly as big as AB, then we showed that those two triangles are congruent and therefore similar. So that's already taken care of. And then if A prime B prime happen to be bigger than AB, relabel them. Call one triangle, swap their namings. And then this is now true again. Okay? So we're not missing any cases by skipping here. Good? Alright. So first thing we did is we picked D on AB such that AB is congruent to A prime B prime. To let M, we'll call that M now, through, oh shoot, I'm going to need a point to talk about that stupid angle. Use red like I was doing for drawing. So over here, so I'm going to let M be the line through D parallel to this, and I'm going to call this intersection point E. You with me on what I'm doing there? So let M through D such that M is parallel to BC, comma, and let E be the intersection of AC with M. Now, once again, technicality I'm not going to put into the proof, but I'll just explain it. How do we know that this point E is between A and C? We can think about putting another parallel line up here, parallel to this line and this line. We know that this line can't cross here and can't cross here, and so it has to be somewhere in between. You good with that? Without getting a full technical argument? You're not good with that? If this went through the point A, so if this parallel line went through the point A, then you would have two parallel lines going through the point A parallel to this. Can't happen.
How is there already one on top?
Let whatever be the line through A parallel to this line.
Okay.
So, we already have a line through A parallel to this line. This line can't go through A because otherwise we're talking about the line DA, which is also the line DAB, which also intersects this. So, a line through D can't be parallel. the line parallel to this through D can't also go through A. How's that? And obviously it can't go through C because it's parallel. It can't intersect this thing anywhere. It can never come down here. And it can't intersect this line anywhere. It can't ever come up here. So it intersects this thing somewhere between A and C. Okay? So there's our point E where it intersects. Next, what do I want to do? Okay, now I need to use this fact right here. Since I know that that number is a rational number, then I know there exists some EF. We're not calling it EF because those are labeled in here, but I know that there exists some unit such that I can say that the length of this is m of those units and the length of this is n of those units. Does that make sense? Using our last theorem. So, since A prime B prime over AB is a rational number, then there exists m and n in Z such that A prime B prime, the length of that is equal to m, and the length of AB is equal to n. So I can find some unit that makes this true. That's what our last theorem gave us, right? So now this is m of those units, whatever they are, and this is n of those units, whatever they are. Good? So now I can come and I can divide this thing up into m parts. We know how to do that now. Except for James, he needs to go home and prove it to himself. But we can divide this thing up into m pieces, and we can divide this whole thing up into n pieces, right? So we divide this thing up into m equal pieces. Just going to pretend that m was 3, and so those correspond to right here and right here. And we can also divide this whole thing up into n equal pieces. And they're all of the same unit length, right? We're using the same length when we measure both these. So my points, when I pick my n points on here, are going to align with those, and then we'll get some more down here. Good? I told you this is kind of messy. So now, what we're going to do is we're going to use this breakup to break up this side into equal pieces as well. So I'm going to draw a parallel line to that point, parallel line to that point. We already got one to that point, parallel line to that point, parallel line to that point, constructing points over here. Does that make sense? So I'm going to add parallel line, parallel line, parallel line, parallel line. When I say parallel, I mean parallel to BC. And then we're going to get points over here. And using our first theorem, we then have that each one of these little segments is congruent. So this side, the ratio, and we did the same thing up here, right? Carrying over the picture. The length of this is m units. The length of this is n units. We broke this up into m equal units, and we broke this up into n equal units. And so now the ratio of this to this is also m to n. Does that make sense? So we showed that this over this is equal to this over this, which is what we're trying to do. Do you follow the thinking there? It's a little bit messy. Now I'm not going to write it all out, partly because I hate this proof. But make sure you understand the thinking. No questions?
Well, how do we get DE proportional to BC, like with the rest of the ratios?
So this,
Yeah.
we can almost ignore drawing it over here. So this is m,
Right?
which we can do here. We know that this line is parallel to this line. So all these parallel lines are also parallel to this.
Right.
So this and this are broken up into equal pieces. M equal pieces. Maybe just write out for a second.
I'm asking how we get the third side to fit into with all those ratios.
This side down here,
Yeah,
you're saying BC?
yeah, BC and DE.
BC and DE?
Because don't we have
Or
to have
B
all
prime,
three
C prime.
sides proportional?
Oh, we could have done the exact same argument. So we're only showing that this side's proportional to this side.
Oh,
We could have taken this triangle, stuck it down here, drawn like that, shown that this side's proportional to this side.
right.
So we were just going to show that too. Okay, so you see how, go back to blue. A prime B prime over AB is equal to AD, because that's congruent to that. Sorry, I erased that congruency. That is congruent to that. That's how we constructed D. We picked D, so that was true. So that number is the same as that number over AB. And then we showed that we could represent that as M over N. Right? Using this information. Which we showed that we can break this up into M equal pieces and this into N equal pieces. Notice this length isn't necessarily the same as this length. We're just using that early theorem that we used right at the beginning. Viewing just these three parallel lines, since this parallel line bisects these two, it has to bisect these two. So we just know that those two lengths are equal because these two lengths are equal. That doesn't mean that that length's the same as this length. So we're using different units for measuring this side than we're using for this side. But there's still n and n of them, is the point. That makes sense? So, we were also able to measure AE over AC with m to n. And then we already showed right at the beginning that this triangle is congruent to this triangle, right? So AE is congruent to A prime C prime. So that's equal to A prime C prime over AC. And so we showed that A prime B prime over AB is equal to A prime C prime over AC, the lengths of those, which is what we were trying to show. You follow that? Kind of messy. Hopefully, can show you the area. Way nicer, way prettier. So that's theorem 9.7. Wow, we still got ways to go. This is a big chapter. A lot bigger than other ones in terms of pages, but just in terms of theorems.
It goes up to like 9 or 10.
And a lot of the theorems was just building up to that proof, which is why it's so annoying to me. Because you could have taken the time to build to a different proof. And it's way more elegant and always works. You don't have to talk about special cases. Okay. Theorem 9.8.
Goes to 15 theorems.
Oh, I think I missed two corollaries. So we just barely showed that if two triangles have all their sides congruent, then they're similar. Not all their sides. Angles. I'm mixing up my words bad tonight. So what we just barely showed is that if this angle is congruent to this angle is congruent to this angle, and this angle is congruent to this angle, then those two triangles are similar. Okay? Now, we get a corollary right out the door. What if I didn't know that that angle was congruent to that angle? What if I just knew that that was congruent to that and that was congruent to that?
Sum of the angles.
Yeah, those two are still congruent because they still add up to a straight angle, right? So you actually only need to know that two angles are congruent in triangles to know that they're similar triangles. And then last corollary they add, which I don't know why it's not the same thing as that, but they specify it.
Well, if one of those was a right angle.
Yeah, they say, what if you only know in two right triangles that this side's congruent to that side? Or that angle's congruent to that angle. So you only know one of the angles, but they're both right triangles. Well, then you know two of the angles, and so you know all three. Right? You see how that follows immediately? I don't understand how this is different from this. You know two angles, but I don't know. They add it as a different corollary, so we will too, I guess. So those are the two corollaries that follow from the proof we just did. Now that proof we just did, you're not expected to know how to reproduce or anything, but you are expected to know the result. If two triangles have all their angles congruent, then they're similar. You need to memorize that fact. And you should probably memorize what it means to be similar. The proportionality of sides. That is so useful. It's amazing. All right. A line that divides two sides of a triangle proportionally is parallel to the third side.
You already proved it.
Nope.
Or you already
We went over something a lot like it. So, if I have A, B, C, so this is theorem 9A. Huh?
Don't draw your line halfway.
Don't draw what?
Don't draw your line halfway through the triangle. Draw it near the bottom. Your middle line.
Oh, that's what you're saying. So, a line that divides the two sides of a triangle proportionally is parallel to the third side. So let's start with that. So if I take a line through here, and I draw it so that, let's give it A, B, C, D, and E. If I add a line here such that AD over AB is equal to AE over AC, so if those distances are proportional, so if I draw a line here so that that to that is the same as that to that, prove that means that this is parallel to this. Okay? And I think there's a second part. This means that if AD over AB is equal to AE over AC, oh, they just finished saying exactly that? Why did I think there's a second part to this? Okay. So, if, kind of doing this a mess, if that is equal to that, then we want DE is parallel to BC. Can't we already do if an angle is congruent with two proportional sides?
I think that was if the, if DE bisects AB. Not with proportion.
No, we did if two angles are congruent. With one proportional side.
Alright. Oh, we're going to use parallel. Okay, I see what we're going to do. So similar to what we did last time. That's why I'm thrown off, is because what I was doing last time is what I was thinking for this one. So we're going to pick a line through D parallel to this already. So we don't know that that's parallel to that. We're going to pick a line through D parallel to this, and then show that it must be this line. Okay? So if I have a line, and we'll say it intersects over here at F. If I have a line DF, so that this is parallel to this, then that gives me that this angle, maybe I'll use red again so we know it's going to the red line. This angle to the red line, not to the blue, is the same as this angle. Corresponding angles. And I know that this angle is the same as itself. So this triangle, so then I have triangle ADF is similar to triangle ABC. You see that? Because they have two angles in common. And now that I have that this triangle is similar to the big triangle, I get the proportionalities. So then I get AD over AB. Let me write it this way first. Let me write my AF one. So now I know that AF over AC is equal to AD over AB. But I already know from my given that AD over AB is equal to AE over AC. That's what I assumed was true. I was showing that if this is true, then those two lines are parallel, right? So I have, since the small triangle is congruent to, or similar, since the small triangle is similar to the big triangle, then that gives me this information. Right? Their corresponding sides are proportional. That's part of what it means to be similar. So this side and this side are proportional, but I already know that this side was proportional to this side, so this is equal to this. So that gives me that AF is equal to AE, that distance. And if this distance is equal to this distance, then what?
EF is equal to DE.
Oh, sure. Or in other words, F is equal to E. They're the same point. So that point and that point are the same point. So that line is parallel to that line. See the proof of that? Should we restart and go over it, or you think you got it? You think you got it? No restart, go over? Okay. So that was theorem 9.8. Theorem 9.9. Does someone just want to read these to me so I don't have to keep going back and forth? Theorem 9.9.
Given triangle ABC and triangle A prime, B prime, C prime with angle A congruent to angle A prime and AB, the measure of AB over the measure of A prime, B prime is equal to the measure of AC over the measure of A prime, C prime. Then angle ABC is similar to, or triangle ABC is similar to triangle A prime, B prime, C prime.
Thank you. That's way better. Alright, so if we have two triangles with one of their angles congruent and the sides on either side of that angle proportional, then those two triangles are similar. So let's draw a picture of this so that we can see what's happening. So we'll draw our big one, and same argument as before. I'm always going to make AB the big one and A prime, B prime the small one. Because if they're the same big, then obviously they're congruent. If A prime, B prime are actually bigger, relabel your points. So we've got A, B, C, and we've got our little triangle. A prime, B prime, C prime. So we know that this angle is congruent to this angle. And we know that this information. And we know that AB over, I like doing the primes on top. I don't know why. A prime, B prime over AB, that ratio is equal to A prime, C prime over AC. Those measures. So this over this is equal to this over this. right? And we need to use that information to show that these two things are congruent. So, not sure what I'm going to do yet, but first thing I'm going to do is I'm going to draw a triangle over here with that segment length. So in other words, I'm going to pick D over here so that this distance is the same as that distance. Right? And let's see, am I going to want to draw a parallel line through it? Why not? So if I put a parallel line through there, so that that's parallel to that, then I know that this angle is the same as this angle. So I know that the big triangle is similar to the small triangle. Now I need to show that this triangle is congruent to this triangle.
You can use our last theorem, I think. Line that divides two sides of a triangle proportionally is parallel to the third side. Oh.
Yeah, I don't have that. Shoot.
What can you use?
What I think I'm going to want to do, let me see. Maybe I need to use the sides? See what the author does? He jumps straight to that's congruent to that.
Well, maybe instead of making that line parallel, we can do the same thing that we did with A prime, B prime.
You think?
A prime,
Just
B
pick a
prime.
point over there? I thought we should be able to jump to that easy enough, but since we're not seeing it, we'll just jump to it. We should be able to see it though. So get rid of that, get rid of that. And we'll start with making this side congruent to that side so that this triangle is now congruent to that triangle.
Now you know that's parallel because of 90.
Oh, now, perfect. Good. So now, using our theorem 9.8, since we know that, we knew that this over this is equal to this over this, right?
Mm-hmm.
Well, now we have this over this is equal to this over this. So this line segment divides these things proportionally, which means that this is parallel to this. And now that that's parallel to that, corresponding angles, I guess do 2, 2, and 3, and 3. And so big, similar to small, congruent to that, makes big, similar to that. You follow that thinking? All right, you want to write it out, or you think you got it?
Write it out.
You want to write that one out? So let's restart. One. Let triangle ABC and triangle A prime, B prime, C prime exist such that A prime, B prime over AB, that length, is equal to A prime, C prime over AC, those lengths. Right? 2, without loss of generality, I hope we say that bad. Generality, I always add an extra syllable for some reason. Without loss of generality, assume AB is greater than A prime, B prime. Right? Same, we've discussed that a couple times now, so hopefully you're good with that. 3. So now we're going to pick our point D over here. And we're going to pick our point E over here. Let Ooh, we're going to have to argue E. And I don't want to go through the big explanation of that. How do I know that AE, how do I know that this is less than this?
Because it lies in between.
If this is smaller than this, then this has to be smaller than this for this ratio to be true. Right? I can't say 1/2 is equal to anything bigger over anything smaller. It has to maintain that ratio of 1 to 2. Does that make sense? So when I force AB to be bigger than A prime B prime, that also forces AC to be bigger than A prime C prime, because we have this given information. Does that make sense? Yeah? No? Alright. So I'm not going to bother spelling that out. And I'm just going to assume that that's how it falls out. So let D and, or maybe we'll do one at a time. Let D on AB such that ADB and AD is congruent to A prime B prime. Let E on AB AC such that AEC, maybe we'll put parentheses, A prime C prime over AC is less than 1. We know that. So AC such that, you see how that ratio being less than 1 is the same thing as that being less than that. So I'm just going to write it that way because then I think it's more clear why that follows. Since A prime C prime is less than AC. So then let E on AC such that AEC and AE is congruent to A prime C prime. Should have put that after I put this. Oops. You understand what I'm saying though? You understand the argument? Okay, so 5. So we've got that congruent to that, and we've got that congruent to that. So 5, then DE is parallel to BC by theorem 9-8. Let's read the exact verbiage of 9-8 again. A line that divides sides of a triangle proportionally. Notice that this divides it proportionally. That over that is equal to that over that. Maybe I should have specified that. But it says if it divides it proportionally, it's parallel to the other side. So then that divides that by theorem 9-8, comma, since
AD is equal to A prime B prime.
AD over AB is equal to A prime B prime over AB is equal to A prime C prime over AC is equal to AE over AC. Follow all that? In other words, AD over AB is equal to AE over AC. AD over AB is equal to AE over AC. Those are proportional. So DE divides the triangle proportionally, so DE is parallel to the other side, namely BC. That's what that theorem said. Theorem 9-8 says that if you have a line that divides the triangle sides proportionally, it's parallel to the other side. Here's the sides that divide it proportionally, here's the other side. Does that theorem make sense? And does it make sense how we're using it? So that we get that this is parallel to this. Okay, once you got that, everything, oh, I guess we need to say that this is congruent to this. Maybe we'll say this is similar to this, then this is congruent to this, and then we'll be done. So next thing we need to say is this angle is the same as that angle, and angle A is the same as angle A, so those triangles are congruent. Similar. Alright, 6. Observe angle B and angle ADE are corresponding angles CA. So, now observe that, comma, and angle A is congruent to angle A, comma, so triangle ADE is similar to triangle ABC. Good? Count your fingers. Still got 10? That's good. Alright. So now we need to say this triangle is congruent to this triangle, and we're done. How are we going to say that this triangle is congruent to this triangle? I guess my picture is missing a piece of information. We knew angle A was congruent to angle A prime. And I guess I didn't specify that here. Let that and that exist such that that and angle A is congruent to angle A prime. We're going to need that piece of information. It's pretty important. So now, this triangle is congruent to this triangle by...
Side angle side.
7. Side, angle, side. Side, angle, side. We don't know that that angle is the same as that angle until we know they're congruent, then we know that. Then, triangle ABC prime 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 is congruent to triangle ADE. Oh, we can use our theorem now. Then, angle A prime is congruent to angle A, and angle B prime is congruent to angle ADE is congruent to angle B. Angle A prime is congruent to angle A, and angle B prime is congruent to angle B. 9. Therefore, can you guess where we're going with this? That's disappointing. What were we trying to prove the whole time? That is a terrible box. Well, we haven't proved yet just because a triangle is congruent to a triangle that's similar to another triangle, that triangle is similar to that triangle. I mean, it's not a hard leap of logic. But, nonetheless, any questions about it? Now we wrote it all out, especially for James. Aren't you glad you came?
I'm always glad.
Then why do you ever not come?
Made fun of me.
Huh? How come I never come?
Yeah.
Tell me.
Classes in a row.
One class.
Okay. Theorem 910 is pretty similar. So the one we just proved, we said if an angle is congruent and two sides are proportional, then they're similar. The next one's going to say if all three sides are proportional, then they're similar. You see what it's adding? So in other words, we don't have this, and we have the last proportionality. What are we missing? BC? line 10. And shoot, too much work to clean up the picture. A, B, C. A prime, B prime, C prime. All right, so let's think about how we're going to do this one. First thing I'm going to do, same thing we always do. Take that line segment, copy it over here, mark that point so that this is congruent to this, right? Now, do we want to draw a parallel line, or do we also want to mark this one? Now, let's mark the second one. So we'll take this, draw it over here, so that this is congruent to this, and now we've got that. Now, since this over this equals this over this, then this over this equals this over this. And we can use theorem 9.8 again, which says if a line divides a triangle proportionally, it is parallel to the other line, which then gives us this angle and this angle are congruent, because they're corresponding angles. And angle A is congruent with angle A, so the small triangle is now similar to the big triangle. Good with all that?
Not with the angle A to angle A. How did you make that leap?
We're not talking about A prime. I'm showing that the small triangle is similar to the big triangle right here.
Oh, okay.
So they both have the same angle A, and then that angle is the same as that angle.
Okay.
So two angles in common, now they're similar. All right. So we got triangle DE, I guess. We got triangle ADE is similar to triangle ABC, right? So now we know that DE, that proportion, better follow the convention I wrote for up here. BC over DE. I now know that all the sides of this triangle are proportional to all the sides of this triangle, right? So I know that this side is proportional to this side. So this length over this length is equal to this length over this length is equal to this length over this length. Right? So I'm just going to say BC over DE is equal to, pick one of the other ones I know, any one of these. Oh, sorry. Start here. Which one should I use? This one?
Mm-hmm.
So it's proportional to AB over AD, right? But AB is the same as A prime B prime. A prime B prime over AD. Oh, oops, I was watching out my AD. That's what happens when I switch how I write it. And put those small ones on the bottom. I put them on top. So AD and A prime B prime are the same size. So that's the same number. And then I'm already given that this, AB over A prime B prime, is equal to this. So that is equal to BC over B prime C prime. Now you see why I did that? Maybe I should have started with this. I have this side congruent to this side. I have this side congruent to this side. I need this side congruent to this side. So I'm doing that this to this is the same as this to this is the same as this to this is the same as this to this. That's what I have here. So that I can argue that DE is the same size as B prime C prime. Do you see how that follows? So I'm just going to go right to it. I'm not going to flip reciprocals. I should have written them different. I hate myself now. All right. So we got DE is now equal to B prime C prime, right? Maybe to show you with the algebra real quick. If I have 2 over x equals 2 over y, that instantly follows that x equals y. I have the same thing over that equals the same thing over that. So those two denominators are equal. And that's what I have right here. In case the algebra's not popping out at you. And so then we got that, and that are equal. So that triangle is congruent to that triangle, so that triangle is similar to that triangle, which is similar to the big triangle. We're done. So triangle A prime, B prime, C prime is congruent to triangle A, D, E is similar to triangle ABC. So that's congruent to that is similar to that, therefore that is similar to that. Good? I'm not going to write that one out because it's real similar to the other one. We just swapped out an angle for a congruent side, and then we had to use side, side, side instead of side, angle, side for congruence. Is that fireworks? What theorem was that? 9, 10?
Yeah, 5 more.
5 more theorems? Can we do it? Theorem 911. Theorem 911 is an awesome theorem. It's one of my favorite little theorems with right triangles. And what it says is, essentially, if you have any right triangle, sorry, that's terrible. Do you know what the altitude is of a triangle? Have you ever heard that term? So here's a vertex. The altitude of this vertex is the line that comes down and meets this side at a 90-degree angle. That's called the altitude.
Okay.
So if you take the altitude of a right triangle from its right angle, it divides your right triangle into similar right triangles. In other words, this little right triangle is similar to this right-hand right triangle is similar to the whole right triangle. And I think that is just one of the neatest little things. So let's see how that works. So let's start by showing that the right-hand side one, that triangle, is similar to the whole triangle. Okay? Notice that they both have this angle in common.
Is this the golden?
And they both have, no. Because the ratio could be anything. So notice that they both have this angle and they both have right angles. So they have 2 angles in common. So they're similar. Do you see it? Using the right triangle, it has this right angle and that angle. Using the whole triangle, it has that right angle and that angle. And so they're similar. Now, looking at the left triangle and the whole triangle, they both have this angle in common. And a right angle.
How do they have the top? Okay, how does the right triangle and the whole triangle have the top angle?
Alright, so maybe down here, we'll redraw the right triangle. And we'll redraw this triangle over some. And we'll kind of get rid of that.
Okay.
So, look at this big triangle and this triangle. That angle is the same as that angle, right? That's a right angle, that's a right angle. You see it now?
Wait, did you just flip it upside down?
I took that triangle and I redrew it right there. I didn't flip anything.
I'm not seeing it.
Do you see that this angle is the same as that angle?
Yes.
Here, let me get rid of this dotted line for a second. You see that that angle is the same as that angle.
Yes.
Pretend they're 20 degrees.
Yes.
That's 90 and that's 90.
Oh.
So that's 70 and that's 70.
Okay.
Similarly, this triangle, they both share this angle, which was 70. That's a right angle and that's a right angle, so that's 20 and that's 20.
Okay.
Now I'll put my dotted line back. Pretty neat, huh?
Mm-hmm.
Now, do you know how many proportionalities that gives us that are equal? you have all the proportionalities from this triangle to this triangle, all the proportionalities from this triangle to this triangle, all the proportionalities from this triangle to this triangle. So you get 3 from this to this, you get 3 from this to this, and you get 3 from this to this. That gives you 9 proportionalities that you now have access to anytime you have a right triangle. You drop its altitude and boom, you have all that information. And this is the heart of the Pythagorean Theorem, is using this. So let's pay attention to a couple of them. So, let me label these points. We'll do the big one, A, B, C, and then that's going to be D. D, D. Are you okay with me relabeling like this?
Mm-hmm.
I'm going to put the D up there. And this is also B. And this is also A. Okay? So we're going to get what's called the... Oh, so it was to prove that those are similar, but I think you see how those are similar now, right? It's more just you got to look at it till you see it, and once you see it, you see it. And then, so that's what the proof was about, but then it gives us something called the mean proportionality. And so one of the things that we see right out the door is, since this and this are similar, let's write how those are similar. Let's write the similarities. I think that will help us identify the proportionalities that we're going to care about. So we have triangle, I'm going to start with the little one, A, B, let's go count, 1, 2, 3, count like that. So triangle B, the 1 angle, go to the 2 angle, A, go to the right angle, D is similar to triangle, on this one start at the 1 angle, C, go to the 2 angle, B, go to the right angle, D is similar to triangle C, A, B. You see how I'm just following the angles? And if you follow the angles, you'll get everything lined up correctly. And now we can use proportionalities just by looking at this without confusing ourselves in the picture. So, I got the proportionality AD, which was in between the 2 and the right, goes to BD. So we go do like this, BD is equal to, and now I'm going to do what BD goes to from this triangle, and that's going to go to DC.
CD.
CD, is that the way I labeled it? I'm trying to look at 2 places at once. So we said AD goes to BD as BD goes to CD. You see that? As long as we make sure we're using the same locations here, then we know it's good for sure. And the reason I did that is I want to use this side twice. So I said this goes to this side as this side goes to this side. But I reference this same dotted line twice. Now I think that this is easier to see with numbers, or with variables for length, so I'm going to re-plug that in with variables for length. So I'm going to call this distance, I'm making a mess of this, let me put my numbers in red. So I'm going to call this distance X, this distance Y, and this distance Z. Z is from here to here, X is from here to here, and Y is from there to there. So relabeling this using those points, we get X over Y is equal to Y over Z, or in other words, we get Y squared is equal to XZ. What does that give us? That gives us that the square of this distance is equal to the product of this distance with this distance. And so, Y is a type of mean. We have different means that we take of numbers, different ways of averaging numbers. This is one of the ways that we average numbers. And I can't think of an application off the top of my head. But it's a useful way of doing it. So there's one of the proportionalities we get. That's not the one that we're going to use for the Pythagorean Theorem. The one that we're going to use for the Pythagorean Theorem is AD, let me go back to blue. Let me see. I think it's that goes to that as that goes to that. Yes. Sorry, I know this seems a little contrived at first, but it will make more sense when I write it out. So I want AD to go to AB, this time with the big triangle, going from small to big. AD goes to AB as AB, maybe I'll write BA here, goes to CA. So
CB.
AD goes to AB
Okay,
as AD goes to AB as AB goes to AC. The small side goes to the small side as the hypotenuse goes to the hypotenuse.
Yeah.
Does that make sense? Okay. Now I'm going to get rid of these letters because we're going to put different letters on there in a sec to help us think about this. So that's one of them. So that was using this, the small going to the big. Now I'm going to use the medium going to the big and do the exact same thing. Well, I don't know if it's the exact same thing, but similar idea. I'm going to do that. This goes to the medium side goes to medium side. So the one from 1 to the right goes from the one from 1 to the right as the hypotenuse goes to the hypotenuse. You see what I'm saying?
Mm-hmm.
So DC, let's see, we're using this one. So CD, that's how I should have said that. CD goes to CB as CB goes to CA. You see that? Now I'm going to plug in letters again so that you can see this in action one more time with variables. So I may call this side A, this side B, this side C, but then this little side I may call X and this little side I may call Y. So C is designating this whole length, A is this whole length, B is this whole length, X is just that portion, Y is just that portion. You understand all my labeling?
Yes.
Okay. So now we're going to have three equations. We're going to have this equation, and then one more that I'm going to write. So we have C equals X plus Y. That's the one more that I'm going to write. That's just saying C is equal to that plus that. That's the easy one. Now I'm going to rewrite these two equations in terms of the variables I just put there. Okay?
Mm-hmm.
So, what's AD?
AD is X.
X. What's AB?
X.
A
Oh.
is equal to BA A over CA C. Perfect. And then let's do the other one. What is it? It's Y over B equals B over C, if you follow it. CD is Y. CB is...
CB
Whoa.
is B.
Oh, that B belongs to that.
Yeah, that's where I.
Don't get confused there. CB is B. We have CB twice, and then CA is C. So are you good with going from these proportions to these equations? All right. Now solve for X, solve for Y, substitute in. So from this equation we have X equals what?
A squared over C.
A squared over C. From this equation we have Y equals what?
B squared over C.
B squared over C. Substituting into this equation we have C equals what?
A squared over C plus B squared over C.
Perfect. Multiply both sides by C. The one theorem that every high school student seems to not completely know. But they can recite this part of it.
How do it?
Huh?
Oh, never mind.
They can say A squared plus B squared equals C squared. But if I were to go along and give them a triangle like this,
and later on.
Yeah, in fact, I could even do it like this. If I call that side A, that side B, and that side C, and I tell them A equals 10, B equals 9, what does C equal? Then they'll go right ahead and tell me, well, C equals the square root of 181. After they do some math. Because they have no comprehension of what that's saying. What that's saying is that the square of the hypotenuse is equal to the sums of the squares of the legs of a right triangle. A leg is a side of a right triangle that's not the hypotenuse. So a right triangle has two legs and a hypotenuse, and that's how we refer to its sides. Okay? So there's the Pythagorean theorem. Pretty cool.
Yeah.
Yeah. I like the more figure-based proofs of it better. The ones with area. This is far from my favorite way of proving it. This is probably my least favorite way of proving it that I've seen.
Where you see the squares on each side?
Yeah.
Yeah.
Because it's very hard to go from this way of thinking about it to seeing what that's talking about with areas of squares. Seeing it with areas of squares is way better. But nonetheless, and maybe he'll give another proof of the Pythagorean theorem when we get to area. I wouldn't be surprised. So I don't know how much theorems we just went through because I just kept talking about the same picture.
We have 4 more.
Converse to the Pythagorean theorem. We have 4 more theorems. We have 2 more.
Nope, goes to 15.
Converse to Pythagorean.
And we're on 13. And we're not going to do 14.
We're on 13.
And we're not going to do 14.
What? Okay.
So let's do the converse to the Pythagorean theorem. This is a real simple one to get. So what they're saying is, so the Pythagorean theorem says that if you have a right-angled triangle, if I have a right triangle, the sums of the squares of the legs is equal to the sum of the square of the hypotenuse, right? What's the converse of that? If I have a triangle such that 2 of its sides squared equals another side squared, I have a right triangle. So let's see how that one follows, and it's a real small proof. Let triangle ABC such that, as a general rule, if you use lowercase a, lowercase b, and lowercase c to designate side lengths, lowercase a is the side opposite angle A, lowercase b is the side opposite angle B, and lowercase c is the side opposite angle C. I didn't follow that convention in this picture because we kind of labeled the points before I knew where we were going with it. So, sorry about that. That was bad on my part. So let A be C such that A squared plus B squared is equal to C squared. So we're saying the side opposite A squared plus the side opposite B squared is equal to the side opposite C squared. Okay? So we've got this triangle. A, B, no, C has to be here now. C, B. So this side is length A, this side is length B, this side is length C. Now I'm going to prove that that's a right triangle. Okay? The way I do that is I create a right triangle, and I make this side the same long as this side, and I make this side the same long as this side. You with me? Then by the Pythagorean theorem, if this is A and this is B, by the Pythagorean theorem, this side is C. And so now this triangle is congruent to this triangle by side, side, side. And so this angle has to be a right angle. You follow that? One more time through. I've got a triangle such that A squared plus B squared equals C squared. I create a right triangle, and I force this length to be the same long as that, and this length to be the same long as that. By the Pythagorean theorem, this side is length C, which is the same long as that. So these two triangles are congruent, so that's a right angle. The converse of it is really easy. Good? And then our last, the theorem that I'm not going to show is the theorem that they use to say if you have two circles and their centers are less than 2 radiuses apart, then the circles intersect at 2 points. That's the one I'm skipping.
Less than 2 radiuses?
Yeah. So I draw 2 circles, right? One radius is from here to here,
Oh.
and another radius would be from here to here. If the circles are more than 2 radiuses apart, they don't intersect. If they're less than 2 radiuses apart, then they intersect at 2 points.
What if they're exactly 2 radiuses?
Then they're tangent to each other and they intersect at 1 point. So you can go through the proof of that on your own if you like. It's just a simple algebra exercise, basically. But I didn't think there was much to be gained from going over it. But the last one we're going over is another one that I think is really cool about right triangles. And it is the one that says that if a right triangle is inscribed in half a circle, if a triangle is inscribed in half a circle, it is a right triangle. What does that mean? That means if I have half a circle, that's exactly half a circle. Don't challenge it.
Looks like what I eat for breakfast.
I don't understand. Oh, an egg?
My eggs are circular, apparently.
And if it's inscribed in half a circle, that means that one of the sides of a triangle is the diameter, and then it has a point somewhere on the circle. Doesn't matter where. Pick a point there, doesn't matter. Construct this triangle, and you got a right triangle.
Yeah.
What if it's in the very top?
Right there?
Yeah.
You got a right triangle. That's the easiest case to prove. We weren't going to bother with that one, but let's do that one first, I guess. So if I've got a triangle, ba-da-da, and that's right smack in the middle, so that it's like this and like this. So then this is an isosceles triangle, right?
Yep.
So then I already know that's a right angle and that's a right angle. Well, how's my best way to convince you of this? Ignore that for a second. Since that's an isosceles triangle, that is congruent to that, and that is congruent to that. Maybe start with that. Then those two triangles are congruent, so these two angles have to be right angles, right? And, oh wait, I can't say that those two triangles are congruent. Let's see. This is the center O of the circle. And so I already know that this side is congruent to this side. And so by side, those two triangles are congruent. So I know that angle is the same as that angle is the same as that angle, and those are right angles. So I know that that and that together are half a right angle. Or sorry, those two together are a right angle. So that's half a right angle, and that's half a right angle. So together, that's a right angle.
Okay, so now prove that one.
Yeah, so now in this case, where O is somewhere over here, O is what we usually use to designate the center of our circle. Label the points how they did. Do you know what they do? A, B, C. I don't even know what page
X,
we're on.
Y, R, Z, R.
Well, those are. Tell me the points first, and then I'll put those numbers.
A, D, O,
Top
B.
is C, under C is D, right
Oh.
is B.
So they're saying come down. Here's D, and this is B. Okay. What do they? Should we use red for lengths again, for numbers again? What do they call this length?
ADX, CDZ,
And just tell me where I'm pointing. Up here.
Z,
Z.
Y.
And then that's R, obviously, and we could also think about this as R. Sorry, am I making too much of a mess of this?
Nope.
Okay. So now in this case, the way that we're going to prove it is to show that this triangle is similar to this triangle. And then the whole thing's a right triangle. Kind of like what we did before. Yeah. So, to show that this triangle is similar to this triangle, I need to show proportionalities. So I want to show that x over z is equal to, ultimately, z over y plus r. Okay? So let's look at what these two things equal. Start with x over z. And I need to pick my variables to write everything in terms of. I think I want to use y's and r's for everything. So I need to write z in terms of y's and r's, and I need to write x in terms of y's and r's. Okay? Because I have too many unknowns right now. And if I'm going to use two equations, I need to reduce it to two unknowns so they have the same variables. Well, I guess oh well. I may write in terms of y's and r's, but what I said I don't think is technically true. So let's start by writing z in terms of y's and r's. Maybe write that as a side note. Z, looking at this triangle right here, is equal to the square root of r squared minus y squared. You see that? Since r squared equals z squared plus y squared, using the Pythagorean Theorem, because this is an altitude, I didn't say that. Altitude. So we already have an angle in common. And so when we're trying to show that these two triangles are similar, we need to show that they have two proportional sides and a corresponding angle that's congruent. And that's how we're showing similarity. Theorem, what was it, 98 again? No, that one was different.
99.
But it's one that we just did. So anyways, I'm showing that this side goes to this side as this side goes to this side, is what I'm trying to prove. That's my ultimate goal. Because if I can show that this is proportional to this is proportional with this to this, that's using both sides of that angle, then we've got similar triangles. And then once I have that those two triangles are similar, then the sum up there is a right angle, because that's a right triangle, so those two angles have to add up to a right angle. And that would say that this angle and this angle are the same. Do you see ultimately where we're trying to get? Okay, so I need to show that this and this are really the same thing. And I'm going to rewrite both of these in terms of y's and r's. So I want to write z in terms of y's and r's, and then I'll write x in terms of y's and r's. But z in terms of y's and r's is like this. Because y squared plus z squared equals r squared. So z squared equals r squared minus y squared, square root both sides. Now technically we could have a plus or minus there, but why do we know that that can go right out the door?
Because you have negative link.
Yeah, negative length doesn't make sense. We don't have negative distances, only positive distances. So we only take the positive case. So you all good with why z is equal to this? Okay. And how do we write x in terms of y's and r's?
R minus y.
R minus y, perfect. This whole distance is r. Get rid of the y portion, all you're left with is x. Okay, so maybe give me more space over here. So x over z, this to this, is equal to r minus y over the square root of r squared minus y squared. Now I want everything under the radical, so I'm going to square this thing and then stick it under the radical. Do you all understand what I mean by the radical? What's the radical?
The square root, right?
The square root symbol. It's called a radical. Perfect. So this is the same thing as the square root of r minus y squared all over. And I'm going to rewrite this in terms of its factors. That's the same thing as r minus y, r plus y. So r minus y squared, take the square root, is just r minus y, right? And then r minus y times r plus y. R times r gives us r squared. negative y times r cancels out with r times positive y, and then negative y times positive y is negative y squared, still under the radical. You good with how we went from this to this? Yeah?
I do.
All right, good. So then, we have an r minus y factor in the numerator. We have an r minus y factor in the denominator. Those cancel out. We're left with the square root of r minus y over r plus y. See it?
This feels so similar or familiar.
Does it feel like algebra?
Feels like trig.
Yeah, this is trig. Trig is showing properties of triangles. That's what it's all about. Anyways, now let's do this one and see if we can get it to look like that. So z, once again, is that. So we have the square root of r squared minus y squared. Sorry, my r looks terrible. Looks like a gamma. Over y plus r. I'm going to do the same trick I did here. I'm going to square it and write it under the radical. R plus y squared. Oops. Oh well. I also changed the order of the terms. But I squared that thing and stuck it under the radical. So the square root of this thing squared is just that thing. So we still have y plus r, or r plus y, doesn't matter. So you good with this transition to this step? Yeah? All right. I'm going to rewrite this same way we did over here. So that is equal to, and I'm going to write just one radical. In case you're unaware, the square root of a over the square root of b is the same thing as the square root of a over b. Those are the same thing. That's a legal algebraic manipulation. So I'm just going to write this radical as one big thing and rewrite the top as r minus y, r plus y, and rewrite the bottom as r plus y squared. Now what?
You cancel them out.
Yeah, the r plus y, I have an r plus y factor in the numerator and denominator. Those go out, I'm left with the square root of r minus y over r plus y. R minus y over r plus y, r minus y over r plus y. One more technicality might be to argue that this is a positive number, otherwise we don't know how to take the square root of it. We don't have imaginary numbers in this class. Is r always bigger than y?
Yeah. Because y is.
Yeah, y is the distance from O to wherever the altitude meets. The altitude has to meet inside the circle, so it has to be less than r. Right? So, r minus y is a positive number. R plus y is obviously a positive number. A positive divided by a positive is a positive. We can take the square root of it. That's valid. We know how to do that. So, the triangles are similar. So triangle, maybe go back to blue. Maybe write out everything we did. Since angle ADC is congruent to angle CDB, that's the way we're going to think about it. ADC is similar to CDB. That's the way those line up. So since that right angle is the same size as that right angle, and AD over DC is equal to CD over DB, AD over DC is X over Z, CD over DB is Z over Y plus R. So since those are equal, since those are proportional, and the angle that they're surrounding, namely that angle and that angle, are congruent, then triangle ADC is similar to triangle CDB. Triangle ADC. So we did this side first, then this side, is similar to triangle CDB. We did this side first, then this side. So this side goes to this side, as this side goes to this side. You see that? Now, since they're similar, we have the rest of our argument. This angle right here is the same as this angle right here, and this angle right here is the same as this angle right here. Since this angle plus this angle is a right angle, or since this angle plus this angle is a right angle, those two angles are a right angle. So this is a right angle and we're done. You follow all that?
Yeah.
That was a big one to end on, but I think that's an awesome one. All right.
Very cool.
Wow. Big chapter. Big chapter, lots of cool theorems. For homework, just do every problem in the chapter and the last two chapters while you're at it. Get caught up. Spend your time doing some geometry.
Memorize the lectures.
Memorize the last two lectures, at least.